This is section 13.4, part D. For our last example in this section, we're looking for the mass of the portion of this cylinder that lies between two planes. And I'm going to have you make a change here. Originally that was x minus 2z equals 4. I'd like you to change that to a negative 6, please. Our density function is 4 grams per cubic centimeter. So I'm going to start by imagining what this looks like. This cylinder is an elliptical cylinder. If I think about the ellipse itself, 9y squared plus 4z squared equals 36. The y-intercepts, if z is 0, looks like y is plus or minus 2. And the z-intercepts, if y is 0, looks like z equals plus or minus 3. So plus or minus 2 on the y-axis, plus or minus 3 on the z-axis, rather. I'm going to actually draw this in dotted because this is going to be the back end of my cylinder. And then this is parallel to the x-axis, since x is not mentioned at all in the equation. So you could imagine pulling this out parallel to the x-axis until you get to the front of the cylinder. There. All right. Now, these two equations are simply planes. Right? They're planes parallel to the y-axis, since y is not mentioned. But what's going to happen is if you think about them as lines in the xz plane, they're slanted in opposite directions because of the opposite signs on the z's. So one's going to cut through like this, the other one's going to cut through like that. And what will happen is you'll get kind of a slanted oval this way. You get another kind of slanted oval that way. And then you're looking for the mass of the part in between here. Now I know it's not a great picture. I did graph this one in Maple. Let's see here. Make that a little smaller so you can see the second one. Come on. Sorry. Hang on just a second. I'm going to pause here. There. Had to redo that one so it was up high enough to get into my recording window. Anyway, here it is plotted in Maple. You'll notice that again I've got the width plots and then I did the implicit plot 3D. There's the equation of the cylinder itself. And then there's the first plane and the second plane. Okay. I've done these in yellow for the cylinder. Red is the first plane and blue is the second plane. So there's my elliptical cylinder. You can see it here. And the two slanted planes we talked about slicing through. So you can kind of see that chunk in between, whose volume we're trying to find. If I think back to front, notice that the blue plane would be the x value in the back, and I'm working towards the front of the x-axis, which is the red plane. So the blue plane was this one, the one equal to negative 6. The red plane is the one equal to positive 6. So let's see here. The back one was the one equal to negative 6. The front one was the one equal to positive 6. If I'm going to think about those as back to front, I'm going to have them solved for x. So I want to think of this one as x equals 2z minus 6. And this one as x equals 6 minus z. So to get my mass, I'll do the triple integral of my density function, which was just the constant 4 this time. And I'm doing dx first, from back to front. The back is the 2z minus 6, and the front is the 6 minus z. All right, next we need to think about the dy and the dx. So our projection of our cross-section in the yz plane is this original ellipse. So I want to think about that next. Sketch it real quick over here. Here's R. And I'm going to go with vertical rectangles again. Again, this is the YZ plane. And if I'm going to go with vertical rectangles, that means I'm doing DZ next. So I need to go from the bottom Z value to the top Z value. In order to do that, I'm going to need this equation solved for Z. So let me do that right up here. Let's see, 4z squared is going to be 36 minus 9y squared. We'll divide by 4 and then take the square root with a plus or minus. So the top would actually be the positive square root. And the bottom would be the negative square root. All right, ugly, but we can make it work. So my lower limit of integration is the negative square root. My upper limit of integration is the positive square root. Okay. So let's see. Finally, I've got dy left. And thank goodness that one's easy to see. Negative 2 to 2. And there we go. There's the setup for our integral. All right. Let's see what we can do. Fortunately, the integrand is easy. My first integral is just going to give me 4x. Until I need them, I'm just going to write that as negative square root, positive square root, since there's no point in writing all that out every time. And then I get 4x, evaluated from 2z minus 6 to 6 minus z. So I'll have 4 times 6 minus z, subtract 4 times 2z minus 6. I'm going to sneak a little algebra in the middle here. This would be 24 minus 4z minus 8z plus 24, which is 48 minus 12z. All right, so I'm going to integrate this dz next, which is going to give me 48z minus 6z squared. And that's evaluated from that negative square root, and I'm going to write it out this time, to the positive square root. Okay. I'll get 48 times the positive square root minus 6 times, and squaring the square root will just give me 36 minus 9y squared over 4. Sorry, I'm off the screen here. My apologies. Subtract. Now I'm plugging in the lower limit, so that's going to give me a negative 48 times that square root. Minus 6 times, and squaring the square root is going to give me the positive 36 minus 9y squared over 4 again. And that's all. Still got a dy after it. All right, let's see what we've got here. These two terms are identical, and I'm subtracting. So those will just go to 0. And then minus a negative makes this plus. So I actually end up with 96 times that radical. And I forgot to do that one out, so we'll have to do this one together. Looks like I'm still in polar mode, but it doesn't matter. A variable is a variable. And even the calculator is going to take me a minute on this one. It's I think we end up getting a pretty large number, and the calculator takes a while to get it iterated out enough to be confident that it has enough decimal places in its answer. There we go. 904.779. And since this is mass, and we were given units this time, that is in grams. So, a bit messier this time in terms of actually doing the integral, but we were able to work through it. This brings us to the end of section 13.4.